Hello and welcome everybody. Today our discussion is going to be on how to find power series solutions to differential equations, okay? This topic is usually not that important in the context of what's been covered in the course, okay? But this, I feel, is one of the outliers where they don't really go deep into the concept and explain what power series is before requiring them to actually apply it, okay? So I'm going to take some time to address what power series is, and then once we have our foundations right, we can get started on making a solution and actually using them to solve differential equations. Okay, so the question of interest that we're trying to solve is this differential equation, which is given to us as y prime of t minus 3 times y of t is equals to 8, and the initial condition given to us is y of 0 is 3. So we're trying to solve this differential equation. You guys know how to do it in the antiderivative way, but we're going to use a different approach here, okay? So before we begin, I have to address, like, what is even a power series? Okay. So a power series is basically a series which looks something like this, okay? It's going to be an infinite series. So your n will start at 0 and go up to infinity, just like how you did in the very beginning of the course. So power series is a series that starts at 0, index goes up to infinity, and looks something like this, which is a coefficient of the nth, Cn, times x to the power of n. Okay, so the expansion of this power series naturally would just mean C0 plus C1x to the power 1 plus t c2x squared plus c3x cubed, and it keeps on going forever. Okay, so the condensed form of the power series notation looks like this, and its expanded form looks like that. So this is what a power series is. Okay, so what we know, which you probably haven't been covering in this course in that detail, but there are functions which we can represent using power series. Okay, so let's say you have a function f of x which could be represented as a power series. Okay, for an example, if I give you an example, the function e to the power x could be represented as a power series like this. So the power series where e to the power x looks like x to the power n divided by n factorial, which when you expand out will look something like 1, because, you know, first time when you plug in n equals to 0, you'll have x to the power 0 divided by 0 factorial, which is 1. Then you would have x to the 1 divided by 1 factorial, squared divided by 2 factorial, x cubed divided by 3 factorial, and it keeps on going. For this particular exercise, we're going to assume that you guys know what this is, okay? So we're not going to go into derivation of how you found out that the power series of e to the power x is this. If you need more help with that, you can reach out to me at any time, okay? But for now, we're going to presume that there's a power series, and there are some functions which could be represented as power series, right? So let's say, naturally speaking, if you have a function, let's say y, which could be represented as a power series, so it could be represented as cn x to the power n, when n starts from 0, goes up to infinity. Naturally speaking, when you take its derivative, okay, with respect to x, the y prime would be represented like this. So remember, c of n is a constant, so that doesn't change. The derivative would be applied on this portion. Okay, so derivative of x to the power of n would result into n times x to the power n minus 1. Starting from 0, going up to infinity. Okay, but the problem here you see is because when you take the derivative, this index is going to cause trouble. Okay, the first term that you would have in this expression at n equals to 0, if you stick to n equals to 0, then that would be x to the power of minus 1, which is not possible, right? The thing with this power series, the first term when you take the derivative should be c1, and then the second term will be c2 times x, and so on. So you're just basically taking the derivative of this infinitely long polynomial. So this is where the culprit lies. So this is the problem. The index cannot start at 0. It must start at 1. And I know it's more obvious to see in the expanded form, but you gotta bear with me. This is how we write the derivative of a function that is represented as the power series, okay? N starts 1. Because if you expand this out, this will look like what? This will look like c 1, x to the power of 0, 2 times 2, x plus c3 times 3, x squared, and so on. And that's exactly how a derivative of this polynomial should look like. Okay. So now that we've matched up how we would find the derivative, I would like to show you an equivalent relationship, okay? So as you know, there are series and they could be interchanged in forms. This y prime, when you start at index 1, could be written like this, but you can also write this as index starting 0. So that would mean you have to shift these formulas inside to match up accordingly, okay? So when you're shifting 1 to the left, you shift all the n's to the right by 1. Okay, it's okay if you don't know this principle. I know they don't really touch on it, but the only thing that you need to know is I'm going to give you a condensed form here. So this will be n plus 1. This will be n plus 1. And now x will be raised to the power of just n. So remember, these two formulas are completely equivalent. Okay, one starts at index 1 and the other starts at index 0. The reason why I want to show you this formula is because we will need that later on in order to combine these expressions together, because they both must start at index 0. Okay, so with that preliminary stuff out of the way, we can now begin solving the problem. How we do that is by actually assuming that our solution is a power series solution and trying to plug it into this equation and satisfy the equation and see what constraints are going to be working with. Okay, one little idea that I want to give you guys before we begin, because okay, let's just do it on the next page. It's easier that way. Okay, so we know if we presume that my y, the function, could be represented as a power series, and I'm just going to point out that, okay, usually people use axis to represent power series. Even though this function is in terms of t, I will solve it in terms of x because I've already given all the information and formulas in terms of x, and I will convert it into in terms of t in the very end. Okay, so bear with me. Don't worry about it. It's just difference variables, but it doesn't really matter too much. Okay, so following on, if you say your y could be represented as a power series, and remember, y is the solution of the differential equation, okay? We don't know what it is, but we know it could be represented as a power series. That's true, which means it could be expanded out to be c0 x squared, c3x3, and so on, right? So if we know this, we already have an initial condition to help us out. We know the initial condition of y of 0 must be equals to given as 3, right here. Okay, so keeping that in mind, because y of 0 is given as 3, if you apply that logic here, which means you're going to sub x equals to 0 everywhere in this equation, and you'll be left with just one term. That would imply that 3 must be equals to c naught plus 0, and so on, which implies that the first coefficient c0 is going to be 3. I'm going to keep this information handy because it's going to be required by us, okay? So we know the first coefficient of this. Now we're going to start to begin solving the problem. If your y is a power series of c of n, x to the power n, I know I'm always writing them out because it's important to kind of be clear on explanations so that we avoid as many questions as I can. Okay, but even though if you have any questions, you know how to reach out to me. Then we also know the derivative of this function could be represented as n starting at 0 going to infinity of c of n plus 1 times n plus 1 times x to the power of n. So we know these two things. Now, given these two things, we can plug it into the equation. The equation of interest is y prime minus 3y is equals to 8. So if you know that your y prime is this function and y is that function, both in the power series representation, you can plug them into the equation and try to solve it. Okay. When you do that, what do you get? When you are yielded with this equation, you'll be given as y prime. So if you plug in the y prime, n0 to infinity plus 1 to the power n. So this is your y prime minus 3 times the y value. So y value is just the power series right here. 0, bring up to infinity, c of n to the power of n, and this must be equals to 8. So all I did is literally plugged in whatever was y prime with this guy here, and whatever was y with this guy here. And now I have this equation. A little bit of algebra will help you combine these two things, and now we'll just condense into one singular sum on the left side. N equals to 0 to infinity. So you'll be left with n plus 1 times n plus 1 minus 3 times give n times x to the power of n must be equals to 8. Okay, so I factored out the x to the power of n, and I'm left with this expression inside. Okay, so this is going to be our key situation. This is what we're going to be focusing on to solve the whole problem. Okay, so let's move on to the next page and move that in the idea. So here, the condition that we're imposing on this equation is from n equals to 0 up to infinity of plus 1 times n plus 1 minus 3 c of n must be equals to 8. So this equation is telling you that whatever is on this side, okay, it's a polynomial, it's a power series. This power series must be equals to 8. Okay, so what does that mean? When you have this condition, this kind of simply implies that if you would have a power series on the left, which is an endless polynomial, and you have a power series on the right, which is just a constant, then you know the polynomial on the left must only have one singular constant non-zero coefficient, which should be 8, and every other coefficient of x must be 0. Okay, so if you see any x terms on the left side, their coefficients should be 0 because there are no x terms on the right. Okay, so let's try to first of all find the coefficient of the x to the power 0 term, which is also the constant. Okay, you can find that out by plugging in n equals to 0 in this expression. So when n equals to 0, the term that you're looking at will look like c1 times 0 plus 1 minus 3 times c of 0 times x to the power of 0. Okay, so this is the constant term we're looking at. When you plug in the n equals to 1, you'll have other terms expanded out there too. But we're going to see this must be equals to 8. So this implies a condition that we have on C1. So C1 minus 3C0 must be equals to 8. So from there, you can easily deduce the C1 must be equals to 8 plus 3C0. And that would yield, because of the given condition we already solved for C0, because C0 is 3, we're going to use that information. And it will be 8 plus 9, which is 17. So we found the first coefficient, which was 0, and now the C0, which is 3, and now the second coefficient, which is C1, that's going to be 17. So we're so far stitching this solution, okay? So this solution, we've found out that this number must be equals to 3, and this must be equals to 17. Okay, so far I found these two numbers, and of course this could be a good stopping point if you want to look at the multiple choices and get yourself a correct answer, but I will take one more step to kind of show you where are we headed to. Okay, so I'll show you what happens to all of these other terms in just a second. Okay, so given that this key idea, we're only going to equate the coefficient of x to the 0 to the 8, that's the only coefficient alive. All the other coefficient of x's should be 0. Okay, so for n values that are going to be greater than or equals to 1, we know all of those coefficients, which are literally these guys, must be 0. Because there's no x terms on the right side. There's only 8 on the right side. So with that being said, we have c n plus 1 times n plus 1 minus 3cn equals to 0. This will give you a recursive relationship. And a recursive relationship is basically going to use the previous coefficient to find out the next coefficient. And you can easily deduce that here. From here, you can find out c of n plus 1 is going to be just 3 times the c of n divided by n plus 1. So which means that if you want to find, let's say, C2, because we already found out C1. So if you want to find C2, that would be equals to 3 times C1 divided by n plus 1s, which is going to be just 2 as well. So it will be 3 over 2 times C1 was already 17, so that's 17. Similarly, you can find C3 by using the same algorithm. You'll be like, C3 is just 3 over 3 times C2. And when you plug back C2, which is right here, you would get 3 over 3 times 3 over 2 times 17. Okay, and so on. So we don't really have to find all these coefficients. I'm pretty sure you guys can see how you found C1, C0, C1, C2, C3, and those should be good enough to kind of predict what you're looking for as a pattern into the original equation. Okay, so now we're going to be using that idea to answer part A, and that's how we're done with part A. The more tricky part is to actually work on part B, where you have to now recognize this power series that you just got and now deduce a commonly known function out of it. Okay, so I'm just going to put this out there to kind of just see what we have. Okay, our power series y of x, remember I'm using x, your variable is a t, don't worry about it, we're going to change it to x in the very end. Okay, so y of x, the first coefficient, so it's basically, I'm just going to write it out in the first form, 1x d2x squared c3x3 and so on, right? And we've figured out the values of c1, c0, c2, c3, so we're going to plug them in there so we can kind of see the pattern. Okay, so what we see is going to be 3, the second is 17x, and then you would have 3 over 2 times 17 x squared. And then you have 3 over 3 times 3 over 2 times 17 x cubed. And I'm intentionally putting it up in this way so that we'll be able to see those patterns easily. Okay, so before we go ahead and try to find a random function this power series represents, we need to know one single very important fact about this course. Okay, because you worked with equations like these before as well, these equations kind of fall under autonomous categories. Okay, because this differential equation is an autonomous differential equation, we already know that the solution y of t must somehow look like an exponential function. Okay, so we know that the solutions for autonomous equations are supposed to look like exponentials. So given that information, we can use the fact and try to somehow see the function's exponential function's power series in the expression that we have. Okay, this thing will take some time to decipher, so I'm going to try to make sure I show you all the steps so you can follow along and deduce it yourself too. Okay, let's go back here and start to see. So I can see that the extra 3 in the beginning could just stay there, and I'm going to try to manipulate this expression a little bit one by one to show you how these things are working out. Okay, so I'm going to keep this 3 outside the picture. I'm going to put y of x here so that we can keep track of it. And out of this remainder, all of these guys, I'm going to factor a 17. Once you factor a 17, you'll be left with x, and then a 3 over 2 x squared, and then a 3 over, basically I'm just going to try to make sure I keep this pattern here, and so on. That's what we're left with. Okay, one thing that should catch your eye is the denominators for these expressions should be factorials. Okay, remember the only thing similarity we're missing on this, if I go back to the exponential function, first of all, we're missing out on the first term 1. That's okay, we can add it up later. I'll show you how to do it. But all the other terms much match this idea where you have x to the power 1 and a 1 factorial on the bottom. If it's a square, then it's a 2 factorial. If it's a power 3, then it's a 3 factorial, and so on. And we are already seeing this pattern in this equation. Okay, I'll show you. Because if you see there's an x squared here, you see a 2 down there. 2 is literally what 2 factorial is supposed to be equals to. When you see a 3 there, you have a 3 factorial because 3 times 2 is literally the value of 3 factorial. X to the power 1 has a 1 factorial, and 1 factorial is just literally 1, so you don't have to really see it. So I'm going to try to put those in different colors so you can see that pattern happening, okay? So y of x so far has been looking pretty good. 17. So I'm going to here subtract and add a 1 in order to make this thing work, you know, in the fashion, okay? But before doing that, I'll show you one trick and then I'll do it later on. So we'll just hold on, okay? Let's go baby steps here. So this is x divided by 1 factorial, 3 x squared divided by 2 factorial. Remember, this 2 is just 2 factorial. Plus 3 times 3, or basically 3 squared, x to the 3 divided by 3 factorial. And it keeps on going this way. So we know that the numerators are matching up. The exponent of the numerator is matching up with the denominator factorial. So that's kind of half of the pattern true. But we have to still deal with these extra 3's hanging out there. Right? So we have to kind of somehow fix this. What I see right now, it could be a little tricky. And it's obvious if you guys don't see it in the beginning. But that's why I'm making a video on this, to make sure you have a good understanding of why things are happening and how they're working. Okay? We see there's a difference between the exponents of 3. Okay, in this case, you have a 3 to the power 0. That's why it's just 1 when you have x to the power of 1. You have a 3 to the power of 1 when you have x squared. You have a 3 squared when you have x to the power of 3. So there's a difference of 1 between the exponents of x and exponents of 3. Okay, what I'm going to do is, if I make sure that these exponents are the same, then I can put them under a same tree of exponent, and I'll show you what I mean. Okay, I want to raise all of these 3 by 1 power so they match up with the exponent of the x. And how can I do that? All I have to do is just divide and multiply by an extra 3 outside the function. So I'll do it here. I'm going to use a different color. So if I multiply and divide by 3, so I'm going to have 17 divided by 3, and now everything is going to be multiplied by 3, so it'll be squared, this will be cubed, and so on. Once you see this thing happening in front of you, it's going to ring some bells. I'll show you. Once you manipulate this a little bit more, you'll be left with 3 plus 17 over 3. So now I'm going to try to move them in the same brackets. Okay, this will be 3x to the 1 divided by 1 factorial. See? Then you have 3x squared divided by 2 factorial. And then you have 3x to the power of 3 divided by 3 factorial, and so on. And this kind of really resembles a function. Okay? Because remember, I don't know if you guys have learned it before, but I'm going to show you. If you have e to the power of x written like this, right, where whatever that thing is lands up here in terms of x, then you can also know that if you want to write the expression of e to the power of 3x, then that would mean a summation from 0 to infinity of 3x to the power n divided by n factorial. So whatever was x now gets replaced by 3x. So that would look something like this. You'll have 3x to the power of 1 divided by 1 factorial. Remember, there's a 1 here too. Plus 3x to the power of 2 divided by 2 factorial. Plus 3x to the power of 3 divided by 3 factorial. And so on. This is precisely what we have. But we're just missing this 1 here in our actual expression. So why don't we just go ahead and do it? Okay, so coming back here, we're missing a plus 1 here, right? If this was a plus 1, then we know this is just an expansion of e to the power 3x. But how do we add that thing? We're going to just add and subtract it. Okay, so what we're going to do here is just use this expression with 3 plus 17 over 3. I'm going to subtract 1, and I'm going to add 1 to this expression so I can complete the expansion. And so on. 3x to the power of 3 divided by 3, and it keeps on going. So now this portion, as we suggested, all the way till the end is just e to the power 3x. And this is how you decipher what function it represents from a generic power series. So this is purely algebra. It's based on algebra, based on farsightedness. So I used a couple of facts. I'm going to recap for a second, and then I'm going to finish up the solution. So the only intuition that I had is because this function is a power series, this function is supposed to be an exponential because we're dealing with an autonomous differential equation. If this function is going to be an exponential function, then I know what pattern I'm hunting for. Okay. When I start to gradually see things that could be factored out, I factored out 17. I automatically saw the factorials repeating themselves. So this was 1 factorial, this was 2 factorial, this was 3 factorial with a 3. So I know we're leaning towards exponential functions because this kind of matches the exponential expansion. So now with that being said, then I recognize this was the cheeky part where you have to recognize how do you combine whatever you see up top under one single bracket. Because once you can nest it into one single bracket, then you can easily go and deduce the expression. Okay, so that's where you had to know how to multiply by a 3 and divide by 3 so that you can have an extra 3 so that these exponents of 3 and x both match up so they can be combined under one single roof of an exponent. And with that being said, the cherry on the cake was just having this extra 1 added up and giving us a perfect expansion of e to the power 3x. Now, the final thing is very easy. All you got to do is just resolve this expression a little bit to get to the final result. So we have 3 plus 17 over 3 with a negative 1 and e to the power 3x. So all of those terms are now just going to be condensed into this e to the power 3x function. And now we have to just expand it so we can make it look nicer, which is going to be 3, basically a minus 17 over 3 and a plus 17 over 3 e to the power of 3x, which would yield into your y of x being, if you resolve this expression, you would get 8 over 3 plus 17 over 3 e to the power 3x. And this is how you make sure you get to the function from the power series. So remember, I did this problem in terms of x. The final solution should be in terms of t. So the y of t, whatever they're looking for, is 8 over 3 plus 17 over 3 e to the power 3t. And this is how you wrap up this thing. How do I know did I get the right result? You can also double check your work using the antiderivative way. So I'm going to do that here to just double check if I got the right result. Okay, so my differential equation was y prime minus 3y equals to 8, and the initial condition was being equals to 3. So if you rearrange this, you get y prime equals to 8 plus 3y, and if you take this, you'll be given dy by 8 plus 3y equals to d. Integrate both the sides, you get ln plus c by 3. I'm not going to work it out for you. I'm just trying to make sure that you can see the work, follow along, and check it, okay? You can do it yourself too. I'm pretty sure you guys are capable of doing this. So ln of 8 plus 3y must be equals to 3t plus c. So taking exponentials of both sides leaves you with this on this side, e to the power 3t with a capital C in the front. Okay? If you don't know how I got this, I'm pretty sure you guys can follow along with your method and you'll be able to get the same result. Okay? From here, you can isolate for y being c e to the power 3t minus 8 divided by 3. Okay? That's the general solution. And now we know that the initial condition of y0 being equals to 3, if you plug it in to solve for c, you would get 3 equals to c minus 8 divided by 3. So that would mean that c needs to be equals to, then a 9 must be equals to this. I think we're getting onto something, but I'm doing something silly with the algebra. Let me just double check. Okay, yeah, so that's kind of kind of thing we're looking at. Okay, c should be equals to 17. Okay, if you solve for that expression for c, you get c equals 17. Plugging back into the general expression will leave you with y being equals to 17 over 3 e to the power 3t minus 8 over 3, which is precisely what we got here. So that verifies that our result is correct. And of course, this was like an algebra kind of jargon, and I'm pretty sure you guys should be able to get to this whole idea very easily. Okay, so all of this content and this document could be easily found out in the description of the video if you want to follow along with your work. Try to work it out for your own version. If you have any questions, you can know how to reach out to me, and I hope this video helped you guys. Thank you so much for watching.